Imagine sending a video call to a friend across the globe, or downloading a huge file from a server thousands of miles away. Your data travels at incredible speeds, often across vast oceans, through a complex network. But how does information that begins as electrical pulses on your computer manage to journey through the internet's backbone as light, and then seamlessly reappear as electrical signals at its destination? At its core, optical-electrical conversion is the indispensable process that transforms light signals, which are the carriers of data over long distances in fiber optic cables, into the electrical signals that digital devices and processors need to understand and use. It acts as a vital bridge, translating the language of light into the language of electricity, ensuring your data can traverse the physical and digital realms of the internet. The fundamental need for this conversion stems from the inherent strengths and limitations of different transmission mediums. Optical fiber excels at transmitting information over immense distances because light, made of photons, experiences minimal signal loss and is immune to electromagnetic interference, allowing for extremely high bandwidth. Conversely, the vast majority of our digital devices, including computers, routers, and servers, are built upon semiconductor electronics that process information using electrons and electrical currents. These devices operate on the precise voltage levels and current flows that define the binary language of zeros and ones. Without this crucial conversion, the light-based long-haul network and the electrical-based computing world would be entirely disconnected. The journey of an optical signal transforming into an electrical one typically unfolds within sophisticated receiver modules, often located in critical network infrastructure like cable landing stations or data centers. First, the incoming light pulse, carrying encoded data, strikes a photodiode. This specialized semiconductor device converts the incident photons into free electrons, generating an electrical current whose strength is directly proportional to the intensity of the light. Following this, a transimpedance amplifier, or TIA, takes this very weak and often noisy electrical current and amplifies it, while simultaneously converting it into a more robust voltage signal. This voltage signal is still analog, meaning it varies continuously. Therefore, the next crucial step involves an analog-to-digital converter, or a DC. A DC samples this continuous analog voltage at incredibly high speeds and quantizes it into discrete digital values, effectively translating the analog signal into the binary electrical pulses that digital circuits can readily interpret as data, completing the conversion. Modern optical-electrical converters are engineering marvels, incorporating advanced techniques to ensure maximum data integrity and speed. Beyond the basic light to electricity translation, they often include sophisticated digital signal processing. This allows them to compensate for phenomena like chromatic dispersion, where different colors or wavelengths of light travel at slightly different speeds through the fiber, which can distort the signal over long distances. Techniques such as electronic dispersion compensation, or EDC, are employed to counteract these effects. Furthermore, some high-performance systems utilize coherent detection, a method that mixes the incoming optical signal with a precisely generated local light source, allowing for the extraction of more complex information and enabling significantly higher data rates and longer unrepeated transmission spans. Ultimately, understanding optical-electrical conversion reveals the intricate design that underpins our interconnected world. It is the unsung hero that seamlessly translates gigabytes of light across continents into usable electrical data, bridging the gap between the speed of light and the computational power of silicon. This critical process ensures that the physical internet backbone, with its vast optical networks, can effectively communicate with and serve the electrical domain of our digital devices, making global communication not just possible, but instantaneously reliable and incredibly efficient.
If you love understanding how the web works, like, subscribe, and stay connected with us.